Hey, welcome back. Now, our next speaker is Mr. Jorge Arroyo, and he will be giving us a talk on the local interactions influence spread of predatory and a predatory system of group events. Thank you, Jorge. Go ahead.
Thank you, Fabio, and thank you everyone for coming. So I want to start my presentation by discussing what group defense is, which is one of the main dynamics I'm going to study in this work. So group defense is usually thought of in terms of animal prey populations, in which at high population densities, prey are able to reduce the per capita predation intensity that they experience. One of the examples that we have in nature is for example, zebras are other herding animals that when they are at high densities, they can confuse their predators by the large number that they have, for example. But I'm going to talk more in terms of consumers and resource in this talk, because we also see some sort of group defense in some plant populations. For example, in kelp forest, which is the system that I work with, we see that the kelp grazers, such as sea urchins, reduce their grazing intensity when kelp is at high densities, because kelp becomes a good habitat for the predators of these urchins. So we see something similar to the group defense that we see in animals. We also see it in plant populations, and we can talk about this in terms of consumers and resource. So to explore the spatial dynamics of this resource population, we can use integral difference equations, which describe population densities in a continuous space and a discrete time. So we are going to assume that the population grows using a growth function f, and then it's going to disperse following a distribution kernel k. This is a contrast from the more classical reaction diffusion equations, in which the reaction diffusion equations assume that population disperse following a non-Gaussian distribution. When we work with integral difference equations, we lose the time continuity, but we can work with different dispersal kernels, not only Gaussian type. So in the model that I'm going to work with, we track adult consumer populations and resource populations over the spatial domain omega and the natural numbers in time. So we're going to assume, since I'm interested in working with kelp, I'm going to assume that adults have limited movement compared to juveniles. So for example, kelp seeds can move over the ocean, and also urchins, the larvae are highly motile, whereas the urchins, once they become adults, they are not that motile. So we are going to have this limited movement of the adults compared to the juveniles. We're going to have that adult consumers consume adult resources, and we are not going to model the juvenile dynamics. We're just going to see the outcome in the adult population. And to model the group defense, we're going to assume consumption follows a type 4 Holding functional response. So type 4 is a special type of functional response in which consumption intensity decreases at high resource populations. So let's start by looking at the model in mathematical terms. The consumer population P, we're going to have a fraction of it surviving at the next step. This is the non-spatial part. And then the spatial part is going to be a consumption response. So here we have the type 4 functional response. We're going to have that the adult consumers produce juveniles through consumption, and then those juveniles will disperse following a kernel KP. Similar for the resource population, we're going to assume that a resource, the adult resource, a fraction of it survives by delta n, and then another fraction survives predation or consumption, which is this exponential term that we have here, and we see again the functional response. Okay. And for the juveniles of the resource, we're going to have that they produce R juveniles, and then a fraction of them die because they are not able to mature before they are consumed by the consumers, and then another fraction is going to die through intraspecific competition. And those consumption of juveniles by adults in intraspecific competition happen locally, but the juveniles of the resource are also produced globally, and then they disperse. So all of these events happen when they settle, but first they disperse through this kernel Kn. Before I show what questions we have for this model, I worked previously in this model using a non-spatial model, which has 4 fixed points, an unstable extinction, a resource-only fixed point, and 2 coexistence fixed points, which are going to be P up hat and N up hat, and P down hat and N down hat. And the lower fixed point is not that important. It's always unstable. And the upper fixed point exchanges stability with the resource-only fixed point at a transcritical bifurcation value for gamma P. Gamma P is the consumption reproduction. So when consumers reproduce pretty quickly, they change its stability with this from the resource-only fixed point, which becomes unstable, and then they are able to invade. So they move to this upper fixed point, which is where the stability exchange occurs. And that's the formula for the conversion rate. So the conversion rate depends highly on the carrying capacity of the resource, which is this fixed point over there. So this is one of the results that we're going to need for the results of this work. We have 2 research questions for this work. Can dispersal induce instabilities in the resource-only fixed point when we have then the current capacity being stable? And what is the impact of varying the parameters of the model in the spread rate? At the end of the day, we want to talk about spread rate of kelp. So when kelp spreads faster, we can think of that as increasing the density of the kelp forest faster as well. So we want to see what variables have an impact on the spread rate. So we're going to, for the dispersal induced instabilities, we're going to assume first that our kernels are probabilities and they are convolutions. So convolutions are that the kernel doesn't depend on the 2 spatial points. It just depends on the distance. And they are probabilities. That means that when you integrate them, they integrate up to 1. With these 2 assumptions, we can take the Fourier transform of the linearized system. And when that linearized system becomes unstable for some frequencies of the Fourier transform, then this means that the dispersal will induce an instability in the system. So what we find is that the dispersal kernel of the juveniles, when it's Gaussian-like, So it's something like what you will get in a reaction differential equation, for example. Then the spatial version remains stable. There's no way that this dispersal makes the instability. But if we choose a fatter dispersal, a fat tail dispersal, such as the double gamma distribution, which is given by this formula, we find that a sufficient condition for a dispersal-induced instability is that the mortality, the proportion of the adults of the resource that survive to the next time step is high. Though the proportion is low. So that means that mortality of the adult resource is high. And this 1/17 that we find is just an upper bound, but it's not necessarily the minimum. It's not necessarily the supremum. Okay. And how does this look like? Well, let's look first at the eigenvalues of the instability of the resource only fixed point, but we're going to look at it at different frequencies because we're looking at the Fourier transform. So when the mortality of the adults is low, we see that the eigenvalue is not able to cross the critical values of 1 or -1. But when mortality is high, we see this region here where it crosses, and that induces an instability in the system. So how does that look like? As expected, when mortality is low, we see that the population remains the same. It remains at the current capacity constantly through space. But when mortality is high, we see these oscillations where we have regions of high density and low density of the resource. One of the interesting things here is that even at this case, the predators or the consumers are not able to invade. They remain at low population densities in all the spatial locations. For the spread rate of resource, usually you calculate the spread rate by looking at when the extinction fixed point becomes unstable. But in our system, the extinction fixed point is always unstable. So we cannot calculate the asymptotic spread rate using the traditional methods of integral difference equations. So we have to study the spread rate using a numerical scheme. So we're going to put our population or resource 0 everywhere except at a point A, where A is the point of the 20% extent. And we're going to assume that our consumers are constant for space. Those are our initial conditions. And then we calculate the time M that the resource population takes to reach 80% of the current capacity at the other side of the line of the domain, which is at some point at the 80% of the extent of omega. So we go from 20% to 80%. It's also better to illustrate this with a figure. So on the left, you can see the initial conditions of our system with a constant density of the consumers at some level P0, and with the resource at a current capacity at a single point. And after 30 time steps on the right, you see how it looks. And in this case, the time M that it takes to reach 80% of the current capacity at the other side of the domain is around 28 time steps. So the one on the right that you're seeing is more or less the end result of our numerical scheme. And we get some pretty intuitive results. For example, if we increase the consumer density at our initial condition, we see that it takes longer for the resource to reach that point that we said is the threshold. And also, as the resource produces more and more juveniles, the time decreases. Those are results that are pretty intuitive. But also, we get some pretty unintuitive results. For example, when consumers produce offspring, like how many offsprings are produced by the consumer, doesn't have a significant impact on the spread rate of the resource. And you can see here that this red line that we have here, the red dashed line, is the point where the bifurcation occurs. So the transcritical bifurcation that I was talking about earlier in the talk. And it turns out that this doesn't have an impact on the overall spread rate of the resource. So both when the consumer is able to invade and when the consumer is not able to invade, we see the same outcome. It doesn't have an impact on how fast the resource spreads. And the other interesting result here is that when group defense increases its intensity, we see that it takes slightly longer for the resource to reach the other side of the line. This is a pretty intuitive result because as group defense increases, one will expect that it goes predation decreases, but it turns out that there's something else happening there. And what we get is that intraspecific competition is actually having a bigger role in slowing down the spread rate of the resource. So to summarize, can dispersal induce instabilities? When we have fat-tailed kernel distributions, such as the double gamma distribution, yes, we can induce instabilities at high resource mortalities. And what is the impact of varying the model? Oh, and in this case, even consumers are not able to invade in this case. And what is the impact of varying the parameters of the model? We see that group defense leads to a higher impact of intraspecific competition, and the resource population slows down. So intraspecific competition becomes more important as group defense becomes stronger. And that the transcritical bifurcation has no impact in the spread rate of the resource. So just to conclude, we found that our main result is that group defense slows down the spread of the resource population, and this happens at a local scale, which is pretty interesting. And one possible biological explanation is the one I mentioned, that intraspecific competition increases as group defense increases. Another one that is not modeled in this work, but is modeled in a completely separate work, is that group defense may reduce the energy available for reproduction. So at the end, as group defense increases, the resource has to spend more energy defending themselves than reproducing. And that's another explanation found in a different study from the one we did. And overall, we find that IDEs provide a useful method to describe the spatial dynamics of implicitly staged structure population, as this one, where juveniles are part of the system, but they are not explicitly modeled. And thank you. I would like to thank my advisors and co-authors, Alan Hastings and Marisa Basket, and the University of Costa Rica for their support during my PhD. And thank you.
Thank you, Jorge, for your talk. Now we'll go ahead and ask the audience if they have any questions or comments. Let me see if there are any questions in the chat. just a reminder that every speaker has an online, has an option where where the audience can ask questions. If there are any questions that may arise later on. If not, well, thank you, Jorge, for your talk. And we'll start our plenary talk at 11 in approximately 10 minutes. Thank you, Jorge.
Thank you.